Hi everyone, this is Shubro and I'll be explaining fine tuning here. So I've been working on fine tuning for quite a while now, and I thought why not to put out a video on fine tuning and explain all the basics stuffs, what is going on. So yeah, here's a video, and the chapters will be like this. So I'll talk about the introduction, why is fine tuning required, and why do we need, and how does fine tuning work, and I'll explain you through this long notebook that we have, and yeah, pretty much this one. I'll be explaining you through each and every lines of code. So yeah, let's get started. Like, why do we need fine tuning and what is even fine tuning? So if you have worked with large language models, you know when companies need this large language model, maybe for any kind of reasons, like they want to put it on chatbots. Uh, you want your large language model to speak in a certain way so that it responds to customers efficiently, right? But large language models do need to learn how to respond to it. And the most probable way of doing it is basically fine tuning it. Now, there are a couple of ways you fine tune. So you can basically fine tune the whole model. You can do parameter efficient fine tuning. And inside parameter efficient fine tuning, there are other ways like you have low rank adaptation, quantized low rank adaptation. So we can talk about all of them. And so parameter efficient fine tuning is basically a library in Hugging Face. Hugging Face have developed this, and inside that you can get various kind of fine tuning. We will be talking about today is low rank adaptation. And what is low rank adaptation is you can read about it here. Why is low rank adaptation important? How does it work? What does it do? Basically, it adds another layer on top of the model layer. So basically I have this awesome perplexity um, explanation of what is full fine tuning and what is LoRa. So yeah, so the parameters updated are basically a small subset, which is kind of low rank adapters. The memory is high and low here, and storage per task is large and small. Speed is slow and fast. Overfitting, the risk of overfitting is lower here, and the base model is not changed. So when you do kind of full fine tuning, you are also kind of trying to change the weight parameters of the base model, and the base model might unlearn what it has already learned. So what you can do is basically you can use low rank adaptation, and you can add your learnings on top of the base model, and you can kind of not attach that low rank adaptation, and you can also add another low rank adaptations, and you can use one single model and various other LoRa adapters, uh, and you can use this on top of the same model. Maybe you can fine tune your own large language model on, for example, customer support data set, and then you can fine tune it on various other things. Like there are so many kind of data sets, right? In Hugging Face. So let's get hold of some data set, and let's talk about text, right? So yeah, you can see this. Like there are so many kinds of data sets, right? And you can just take in one data set and you can start chatting with, start training, fine tuning on your large language model. That's basically it. You can take multiple data sets and you can have multiple load adapters to train on your large language model. Anyways, we'll come back to the video, and we'll start explaining how do things work here. So we're importing a bunch of libraries here. That is auto model for causal LLM and auto tokenizer. I want to explain you what is auto model for causal LM. So I'll search auto model for causal LM, and you can see this. So auto model for causal LM are basically a type of language model that predicts the next tokens, given that they already have a set of tokens that are provided in the input, right? And the point of causal LM is that they can only see the past and they have to predict the next tokens. So, for example, if you have something like, where is my scary draw? So, if you have something like, hey, how R, and then the next word should, of course, be U. So it's the work of this causal LM model to predict. Now, there are various kind of causal LM models, and what we have done is we have kind of taken this model as today's model. So it's Llama 3.2 1 billion model, and we'll be training it on my Apple computer. So M3 device, M3. So yeah, that's it. So auto model for causal LM is just another class for importing the models, and auto tokenizer is another class for taking in the tokenizer of the same model. Now, what is the function of tokenizer in a model? So the tokenizer basically tokenizes each and every input that you give to the model, and it provides the input to a model in a certain way so that you can pass all these things to the model in the form of integers, and then you can calculate the attention, and then you can predict the next token. We'll come about that. And there are various kinds of tokenizers. So most of the recent tokenizers in today, they generally use subword level tokenization. So if you kind of talk about tokenization in LLM and how do they work, you can read blogs about here. So basically, tokenization is a form of encoding these tokens, these input texts into the kind of input that you want the model to digest. So there are many levels of tokenization. There is like word level tokenization, subword level tokenization, there is character level tokenization, and whatnot. So you can also actually make your own custom tokenizer with like Google Sentence Piece, uh, and you can use these kind of things to basically make your own tokenizer. And there is also like Hugging Face tokenizer, right? So you can also use these things to build your own tokenizer. All right. So yeah, so these are like auto tokenizer to load the tokenizer of this particular model, and we're using auto model for causal LM to basically load this model. Um, I'll just take this video here. Okay, we have this padding equals to left, and we're basically passing the Hugging Face token model ID. I'll come to this thing why is padding equals to left and what is padding and whatever it is. So basically, if you kind of run this, you will, for, in the first instance, you will be seeing that the model is getting downloaded. Um, on further running it, the model is already downloaded, so it will just load the downloaded model. Okay, bfloat16 is the data type that you are using. So there are like float16, bfloat16, various types of data types that we use for loading these models. And yeah, Hugging Face token, simple thing. And pipeline is some other thing that we use to generate inference from these Hugging Face loaded models. So pipeline is basically you have to uh, mention what kind of inference do you want. So what we want is text generation. So we can actually go to the documentation and search about it, and Hugging Face pipeline text generation. Um, I just want to show you the documentation of how it works. So, right. Okay. So yeah, that's there you go. Like this is the documentation of how Hugging Face text generation actually works. I'm not quite sure, I said. Yeah, text generation pipeline, sorry. So yeah, there are like 11 parameters here in the text generation, and you can basically use the Hugging Face pipeline from here. All right, let's go back. So you have initiated the pipeline thing here, and you mentioned text generation. You're passing in the model and the tokenizer, and then in the next sentence, you are passing in the input of what you want the model to speak about. And this is basically the input that you generally put it out through ChatGPT and everything. The maximum number of tokens is that, if you have the knowledge of tokenizer, you will know what is tokens. So tokenizer converts each and every input into tokens, as I said, like character, word, subword level. So you want the maximum number of tokens to be generated out from this. And yeah, this is it. So you can see, hey, how are you? And I will say, hello, is that a code you're a spy? Um, Talking a lot of things. And so that's how, the generation works. And now if we're moving forward, and we'll talk about things, how they're working here. So, you know, if you can also pass batches of input, so you can not only pass a single input like this, you can also pass like multiple inputs like this. So you can just have a kind of input prompt, and then you can pass multiple inputs like this, right? um so what you need to do here is basically you need to put this out in a input prompt, and yeah, almost the same thing. And when we are passing this through a tokenizer, we are actually showing you how the tokenizer actually embeds these things and converts them into integer. You can see there are two things, like how the tokenizer actually processes these texts. And you can see that, hey, hello, how are you? And the capital of India. You will see 12,800 is starting, and one, two, three, four, five, six. So there are six tokens, and one, two, three, four, five, six. One, two, three, four, five. Yeah, and there are six tokens. So like basically there are six tokens per line of this input prompt. And basically the tokenizer have broken this down into six tokens per line. Now, we will face an error if you just kind of increase this by two spaces, and this will happen because. So let me just run it in front of you. So if I'm just running it, you'll see we're getting an error here, and the most probable cause of it is okay. Let me just reduce this gap, and let's see what happens. Yeah, have a look at this. So we're just reducing this gap, and it's almost there. And if you just improve the gap, we're getting an error. And that's basically happening because we haven't done padding. So how does this work is basically you pass in the padding token in your tokenizer. So what does PyTorch do is that they take these inputs and they form tensors so that the machine learning models can process them properly. But if you don't have padding here, you cannot make properly formatted tensors, and while tokenizing, these things will break. So what you need to do is basically padding, and we'll go back to the tokenizer that we talked about. So that's why we're doing it padding side equals to left, which means that basically we are padding it to the left, each and every padding that will be there in the tensor. So suppose we have a block of tensor. So the padding that we want to be done in the tensor, that will be in the left side of the tensor. And we're also initiating two more things. So the first thing is tokenizer.pad token equals to EOS token. So the pad token will be the end of sentence token. So what do you want the pad token to be? The pad token should be the end of sentence token. That's what is coming from so uh, many LLMs like this Llama 3.2 don't come with pad tokens. You have to basically initialize this with pad token. And after that, you just have to mention padding equals to true. So if I just mention the same thing here, like uh, like the same thing here, if I just kind of copy this and I show you here, padding equals true, and I still have the space here, and you'll see even with the gap here, I'm getting proper tensors, right? So that's how basically padding works and all. All right. Let's come to some other things. How do they work? So we have this input prompt here, and basically I'm telling you that simply adding the padding equals to true and all this solves the problem. Okay. Um, we are cutting out the input IDs. So this time we are basically separating out the input IDs here, and we are kind of trying to see what they are. And when you basically decode them, you get something like this as an output. Now, what is this basically? So you can see that this is how it goes as it is tokenized. So we have this beginning of sentence token, and then you have hello, how are you doing? Tell me. So this is basically the sentence that passed through the tokenizer. And so these are the two sentences that we passed through the tokenizer, and you have this like, hello, how are you doing? Tell me. And then you have this EOT token, beginning of text and capital of India. This is basically how it is done. One more thing, if you have noticed here, is basically we have attention mask. And what is this attention mask is saying is just to focus on those tokens that have a real value, and not to focus on padding token. So attention mask basically tells you on which tokens to focus on with ones and zeros, basically. And for example, if you have this thing, if you have beginning of BOT token, right, EOT tokens and everything, the attention mask tells you to just focus on hello, how are you doing? Tell me, and nothing else, because that's what you need to compute the next tokens, right? Okay. We'll also talk about chat templates and instruction prompts and how do they work. And we'll slowly get towards fine-tuning the model and everything. So we have this apply chat template string representation here. So you can see we have various roles like system user assistant and the content behind it. And basically, in the same way, we are just putting in the text, we are passing it through the tokenizer, and we're generating the tokenized version of it. And we're also putting out through the model, and we're using model.generate. Remember this, we use dot generate to generate the output of the model as we have seen it previously. So yeah, we are using model.generate and maximum new tokens, and we're initializing the pad token to the end of sentence token, and we're decoding the output to see what is the result. Um, this is the kind of result that we get. So you can see most of it is the input. And you see like II from the assistant, that's the last input that we have. And then we are still getting the output here. So you'll be waiting to know where the sunrise is. And I basically told them to speak like a parrot, and you can just tell them to speak like anything. That's how you get it. These are some of the things that the meta people has forcefully integrated inside the response. All right. And yeah, so basically this is the kind of structure that goes into an LLM. So uh, if we take this text that we passed in through the tokenizer, so like this input prompt that we passed in through the tokenizer, this is the whole thing that goes in through the LLM. So this is like beginning of text, start header, um, right? Uh, this is how it goes into the LLMs. Now, if you see the inputs and basically the output, like where did I generate this from? So this is the input when you are passing the text through the tokenizer, and this is the output. That is the model.generate that the model is basically generating, right? So if you see the input IDs and the output IDs, you will notice what is happening here. So the input IDs has this attention mask, and it's telling the model where to focus on and where not to focus on. And you have the whole prompt here that goes into the input. But you can also notice that in the output, we also have something like 12,800. That's all like the beginning of sentence token, right? Beginning of text token. Okay, so now we will talk about how does attention works and everything. So you have this text like hello, how are, and we want it to generate like what's the most probable thing, as I talked about here. Like if you have this thing hello, how are, what do you want basically to generate? So we basically want to generate hello, how are you, right? And basically that you word should have like the maximum probability while we're generating models like this, right? So what does happen is basically if you take this sentence and you pass it through the tokenizer, um, and you basically call in the output that basically what is the output here, and you take the logits, you get the probabilities of all the tokens here. If you take the sentence shape of this logits, you will get it like 1, 4, and 12,800 to 56. So 12,800 to 56 is basically like the vocabulary size, and 4 is the number of tokens that this sentence has been divided into. So hello, how are is basically divided into 4 tokens throughout this tokenizer, and we are basically accessing the last index here. So the last index in the sequence is basically 499. Now, tokenizers have this tokens in their dictionary related to an integer. So basically, the word "u" is 499 in the tokenizers dictionary, and if you kind of decode it out, that what is basically the last index, you can see it is 499. And if you kind of decode what is the last index, you will see it's gap u, so it's u with a space, right? So basically if you pass it through like hello, how are, the most probable answer that you will get is hello, how are you. And if you kind of take out the probability of this thing. So you have to calculate the softmax, and you pass in 499 through this probability distribution, you almost get like 97.66%, so almost 98% with accuracy that the word you will come out. Now, here is one more code where you have you're accessing the vocabulary of this tokenizer, and you're putting it GU. So GU is basically space U, and if you pass it through the tokenizer, you will get 499. So basically, what we have been through this. So 499 in the last index has the highest probability, right? So yeah, that's how some of the matter how attention works and all. Um, okay, training on sequence. So here we basically have a sentence, and we have a tokenizer that we're passing it through. If we kind of batch decode it, you will get the same response. And if we kind of, if you pass it through the tokenizer, you will get this response. And if you kind of batch decode it, uh, you will get this kind of response. It's beginning of text token, right? So let's just kind of like what we want to do here, like how does training work, and we want to understand how things are working out here. So we're taking an input sequence and target sequence of the tensor. So what is input and output sequence basically? So input sequence is basically something where you have this whole token. So in this whole sequence, you want the model to basically predict the next sentences, right? So if we take this sentence, we kind of want the model to predict the next token here. But for example, if we want the model to learn the last few tokens, so what do we do? So basically, we take the input sequence where we have this line. So this is from the start just to the last index, and then we want the model to learn the last token, and then we take from the second last token till the last index, which is the output sequence tensor. So we basically want the input sequence tensor, and we will pass it through the model, and we want the model to learn the output sequence tensor. Okay. That's the whole thing. So we're passing in the question, the prompt, and answer, and we are kind of taking it into a chat template. We're passing it through the tokenizer, and that's the whole thing that we are getting out here. And then I've written a beautiful sentence here. So when we add the answer, we have the entire sequence that we want the model to learn. So basically, pass the entire sequence, and let the model learn on its own. So exactly like what I've told you previously here. Um, so after you basically get this thing, you need to generate a full response text. So the full response text actually consists of the chat template, answer, and the EOS token. We need the EOS token so that the model learns to generate the EOS token and stops generating after the end of sentence. So you get an input of something like this. If you tokenize it, you get input something like this. And you can basically get the input ID and the target IDs here. So the input IDs will actually consist of this. So from start to end till the second last token, which is basically this 22,767. And we will pass in through the second last token and to the last token, that is 12,809, 8009. So what we want the model is to learn to generate the last few tokens. But you can also see that the target sequence is also consisting of the prompt itself. So we need to finalize a way so that during training we and loss calculation we only want the model to learn the few uh, the last few tokens and not the prompt itself. So I've written a very good explanation here, if you can see. So you will see that the target ID also contains the input prompt. Ideally, during training, we want the model to learn the last three tokens and generate the last three tokens, right? And we need a separate way the input prompt from the answer so that the model learns only the last three tokens and not the rest. So we'll find a way how to do it. So um, let's first tokenize our answers, and this is the way we tokenize our answer. So we're taking in the empty string plus the answer, and we're tokenizing it. So we're getting 15, 61, and 2267. So can you see like the last few, what were the last few tokens here? Like in the answer, what do we want our model to learn? So the user is asking basically what is the capital of India, right? And the answer is basically New Delhi. So if you kind of take in this whole response, what do we want it to learn? We basically want it to learn these few tokens. It's New Delhi, right? And that is basically 1561, 22, 767. And so we also want the model to stop generating, after it generates the answer, and hence we need to add the EOS tokens plus answer. So this is tokenizer dot EOS tokens, and we're padding it to the maximum length, and the maximum length will be the shape of the target IDs. So what is the shape of the target IDs is basically this one. This is the shape of target IDs. So you can basically take in that particular shape and frame it like that. So that's how you basically get the whole tokenization. Now, as you have padded it, you can see almost everything is 12,809 except the last few tokens, which is basically New Delhi, what you want the model to learn, right? 12,8009 is basically the end of sentence token. Now there is this thing in the Llama documentation that you have to pad everything with -100. So you have to manually pad everything with basically -100. And we don't want the last token to become the padding token. So like we want the model to learn to generate the EOS tokens so that it stops generating after the EOS token. So it will be 12,8009 will basically manually convert it to the POS token. Now, if you kind of generate this whole thing here into one function, and if you pass in the data, that is the prompt and the target response in into this function, the prompt and the target response. So you get something like this. So this is the input ID, this is the labels that you want, right? And now we will calculate the loss function. So we will use a good old cross entropy loss, right? So we like already have the labels and we will pass it through the neural network. So this is the whole thing. Um, so this is how basically you are calculating the loss here. So if you just write a small definition of what cross entropy loss is, so torch.nn, simple calculation of loss. You're passing in through the response, and you're passing in through the data, and this is how much the loss is to learn basically the word New Delhi, right? So, like, it knows the capital of India is New Delhi, so the loss is not much. But if you take something else, so like let's take it for Mumbai and pass it the loss, so you can see that the losses increased, like it's 1.9062, and it will increase like for the model because it already is trained on something that is New Delhi, right? So the loss is very high for learning the wrong answer or untrained answer. So yeah, that's the whole thing here. Um, okay. So we'll talk about basic fine tuning here and we'll start. So we'll take in with the wrong answers only and we'll see how does things work here. So we have a prompt and we have a target response here and we're basically passing through the tokenizer the same thing, the same code that we used to do and we're getting this response, right? So if we basically pass in through this, that we are not passing in through the target response here. We're just passing in, the prompt two that we have here, and up to the current knowledge date, its output is giving me the output that the president of USA is Joe Biden. I've asked who is the PM of USA. So it has also corrected me that the PM of USA is not the PM, so it's basically the president of USA and it's Joe Biden. But I kind of want the model to learn this sentence that, yeah, so basically what we're doing here is we want to learn once more that how does fine tuning work here. So we're basically outputting the response here, and after that, I want to read all of this for you. So all the model does is to increase the probability or the token that you want to be predicted in the sentence sequence. So the meaning of this is basically, you know, uh, when we are passing in through this sentence, through this word, we basically want the model to learn this word. So all the model does is basically, so inside its sequence, it will increase the probability of this token to be the highest. So it will retrain and retrain itself until unless it gets these few tokens to the highest probability. So it will change its weights and biases to this point. All right, let's talk about something else. Let's talk about the low rank adaptation and how does it work. So the low rank adaptation is basically one more LoRa adapter that you attach to the main model. And as I said previously, you can use multiple LoRa adapters with one single model. You can train it, attach, disattach. What you want to do, you can actually disattach it with model.unload. All right. So from the PEF library from Hugging Face, you have to import LoRa config and get PEF model. And these are basically some of the configurations. So Q projection, V projection, QKV layers. There will be basically six target modules inside the attention layer. So we're talking for the first two. You can reduce this from 32 to 16, whatever you want. So we're basically showing the number of trainable parameters. So the trainable parameters are basically very less compared to the 1.2 billion parameters that we already have. And see, we are only training like 0.2% of parameters, which is very easily trainable on your MacBook. So again, we'll see and train and see how this works. And so it's very simple. You pass the input through the tokenizer. This time we are asking the model who is the Prime Minister of USA, which is the wrong question indeed. USA doesn't have Prime Minister. and we're also making it learn the wrong answer, in fact, right? So yeah, that's the thing. And so without basically passing in through the target response, we are asking the model the true answer, and it is saying that the president of USA is Joe Biden till its current knowledge state. Anyways, so we will basically start the training of this model. So how do you do it? You basically pass in the data, you pass in the optimizer, and you manually train the model with, lost or backward, right? And when you start training, you can see like basically the loss reducing from zero point 0.4 to zero point 0.25 slowly. And yeah, if you just increase the number of epochs and use better hyperparameter fine tuning, so you can get better responses. But basically, this is the whole thing. Okay, all right. And basically, when you kind of use the model again to generate like what is the response, you will get a better answer. But we're using the same model again, but it's not responding properly. Maybe because we have used so less training. Even like 0.2% of parameters are trainable. So like training this much parameters also requires compute. Well, we haven't trained that much, so this video is mostly about how does fine tuning works and how can you do it too. When you basically use this, you will not get the proper response. So you need to train more, basically. So how do you actually fine tune when you have a large data set? So we saw when we have like one or two sentences, like this one, just learning a small sentence. How do you do it? But how do you do it when you have a large data set? So this is the whole process how you do it when you have a large data set. So this is like a customer support response that we have. This is a small data set that we took up from Hugging Face, and you're printing the training data here, and you're seeing how does the structure works, and we're basically seeing a part of the data set here. So it has a query and it has a response, and so basically, for training the model, we want it in a certain format. And so we are structuring it first. So like we have prompt, inside prompt, we have this kind of format, and then we have the target response. So you're using basically a function to generate the same kind of a response. Pretty easy. You can generate it. And when you pass in the data through this function, you get a structure like this, right? So now you have the formatted data that you can pass. Now you need to batch process it and basically pass it through the model to fine tune it. All right. So like this is how your data looks like right now, and we have wrote the small code to train the model basically. So let's just explore it. This is like the last cell that we need to explain. All right. So we have this data set, functions, tools. I think this is not needed anymore. So basically, we have this complete LoRa training function from raw data set. So we're basically defining again what are the LoRa parameters we are getting in the model. We are printing the trainable parameters. We have this trainable data. So we are basically taking in this data set, the query, the response. We're making in the chat prompt, prompt index. We're taking in the training data and we're appending it, right? So so basically, we're taking in the training data and we are kind of appending it. And then we have this thing called we are pre-processing the batch, and the maximum length is basically 512. You passing it through the tokenizer. Um, you're encoding the dataset, mapping the dataset through dataset.map. Simple things like training arguments, you're passing it through the training arguments, and you're basically using the model trainer. That is trainer equals to dot trainer, and then model for training, and you're using the trainer.train model to basically train it, and you're using the save model. So this is how it works basically. For our case, I'll just move it this side. Yeah, so this is how it works actually. So these are some of the logs that we get. So, setting up the trainable parameters, telling how much parameters do we have. Um, this is a sample text format that we get. It's a proper text format, and it's mapping the data set. And yeah, then we have this. We were starting the training, so it's already starting. So when you just start the training, and you can get the model saved, and basically after your training is done, you can get your model, and you can use it for inference purposes. That's basically the whole thing here. Um, yeah, so for my case, like I have stopped the training, my MacBook turns hot. Anyways, yeah, so that's the whole thing.